Welcome to another video from Algebra. We'll be talking about the first lemma. We'll need to prove the generalized fundamental theorem of arithmetic. So what is our setup? Let R be an integral domain and AB be some elements from the underlying set thereof, such that the greatest common divisor of AB and the greatest common divisor of A times C and B times C for some C are well defined. Alright, then the greatest common divisor of AC and BC is equal to C times the greatest common divisor of A and B. Alright, so first observation is that, we observe that the greatest common divisor is defined up to associatedness. Thus, it will be sufficient to show that the left-hand side of the equality divides the right-hand side and vice versa. In other words, we are proving that the left-hand side is associated, or is associate to the right-hand side. And for our own comfort, we will define, we'll put u equal to the left-hand side. Now, if C is equal to 0, then the claim holds trivially. We'll only consider the non-zero case henceforth. Now, by definition of u, u must divide both AC and BC, and as such, there must exist some two elements, say x and y, such that ux is actually equal to AC and uy is also actually equal to BC. Also, I should point out that we only consider the non-degenerate case where A, B are two distinct elements. Now, since A and B are different, then X and Y must also be different, right? We have excluded the trivial, and therefore, C, and since X and Y are different, A and B are different, C must then divide U. And thus, there must exist some, say, z element, such that u is equal to c times z. And now we can substitute cz for u in our in our formulae here. And now, using the cancellation rule, we obtain that z times x is a and z times y is b. Thus, z divides both a and b, and as such, it must divide also their greatest common divisor. This is so because both numbers are equal to the product of the greatest common divisor and some other factor which is different for both of them, right? So if we have some common divisor of both of these, it must divide also the greatest common divisor because it doesn't divide the two different other factors. So we have something like this, that divides GCD. We multiply both sides by c, so we have c times z is equal to c times the greatest common divisor of AB. But the left-hand side is equal to u, and thus the greatest common divisor of AC, BC. Which concludes the first part of the proof. Now on to the second bit. So this was part 1, on to part 2. So we wish to show that the greatest common divisor of AB multiplied by C divides the greatest common divisor of UCBC. Now, since the greatest common divisor of AB divides both A and B, then C times the greatest common divisor of A divides AC, and likewise C times the greatest common divisor of B divides BC. But now, since this number on the left-hand side, pardon me, there was a typo, divides both CA and CB, it must, for the same reasons as I have given before, divide also the greatest common divisor of both numbers. Right, so we have shown that the two numbers are associate, and this concludes the proof.